Okay, so now let us talk about some of the important topics. Again, I am not going to say, I am not going to cover all the topics. Some of the, a few, very few current important topics, challenges and all that in the current nuclear physics scenario. Okay, now the first thing which comes to mind is the unification. Still now, dear students, you have to read nuclear structure and nuclear reaction separately. So you have got different types of models for nuclear structure and nuclear models. So basically what you are doing even in 2025 as of now is basically you are doing model study. Model study for both nuclear structure and nuclear reaction. Why? Why do I have to study model? Because I do not really know about the structure as well as reaction itself. Okay, so I have to use some black box which will show the results. What results? The experimental observations. And that black box is basically the nuclear model. And what is the solution? The solution will be to know the wave function. But we cannot know the wave function. It is too complex. Another way to say this is we do not know the interaction. It's too complex. Not any analytical form. So the interaction, even as of now that we know of the nucleons inside the nucleus, we cannot put it in the form of any analytical form, but in the form of a matrix. So you will say, okay, good. So I can write the interaction in the form of a matrix. Good. That's okay. So the question is, what is the dimension of this matrix? The dimension of this matrix can be crore by crore. That's the problem. And not only that, even in that matrix there will be certain places where you will find some correlations. Okay, so this is yet another issue. And we need extremely large computational facilities. So these are the computational challenges which we still require to properly understand the nuclear reaction. And then just knowing nuclear interaction, just knowing nuclear interaction will not help. Knowing the nuclear interaction, we have to then what? Try to use this and understand the structure and reaction of the nucleus itself. Basically, we need to unify, which is still not possible. So researchers are working in this direction, unification. So computational challenges, unification still not done. These are the issues as of this moment. Again, so nuclear force, another problem, which I told you, we do not know the form. Another thing, when I am trying to use whatever interaction I have to use shortcut. One is nuclear model, another shortcut is I have to use effective interaction. So it's a sort of, instead of taking this entire crore by crore matrix, suppose I take a matrix having dimensions 100 by 100. So it's much reduced. So my interaction is much smaller. This is another fancy way of doing physics. Okay, I have taken something very important out of it which is relevant to my particular case. Another very fancy way of saying things, sort of sugar coating, you can say. And this is what effective field theories or effective theories are all about. And then they're doing computations based on this. Another approach is, now you know the problem with nuclear physics, the number of nuclei, it ranges from 1 to approximately 300. Now this number is too large for few body calculations. And again this is too small for statistical calculations. For statistical you need a very large number, 10 to the power 10, 10 to the power 20 and so on. But the nucleus, the number is not large. So we can't do statistical, we can't do few body. Now of course you do know that even doing 3 body calculations is very difficult. You have to do several approximations. But still, even so, as of now, ab initio methods are there. There are special few body calculations, you can say, using which we can find the structure of very light nuclei. Okay, so ab initio methods. This is one of the things. Next, shape coexistence and quantum phase transition. This we have talked about, right? So, nucleus, a single nucleus, when I am considering the excited state, all the nucleons are going to the higher orbitals and interacting, and the result of this I get excited level spectrum. The problem is that at that time the levels they behave very differently. So at the same energy I can have a rotational band with one moment of inertia, I can have a rotational band with another moment of inertia, I can have a vibrational band with one h cross omega, I can have yet another vibrational band with another h cross omega. So this means the nucleons they are behaving such a way that several types of configurations can coexist, and this is the meaning of shape coexistence. And this is also related to phase transition, because this is sort of transition like solid to liquid, liquid to gas, that is phase transition. Here also this is a sort of quantum phase transition. Why? Because the nucleus itself is a quantum many-body system. Now another issue which is again very important nowadays, hot topic of research, is the influence of nuclear astrophysics on nuclear structure, and again nuclear structure on nuclear astrophysics. Because when we are going to study the stars, the planets that is away from our Earth, okay, various types of stars, we are seeing various types of elements. So how do they came into existence? What was the origin? Right now, think of it. This chalk. Okay, consider one atom of this chalk. Okay, so what was the history? Say one day before, the atom was inside this chalk. Okay, not one day, 1 year before, the chalk was probably not manufactured. So the atom was in some other form, in some other raw material, which was lying there in some manufacturer's warehouse. Okay, not 1 year, 1 decade back. Where was this atom? Suppose somewhere inside Earth. Maybe this atom was a part of some tree. Okay, 1 century back. The tree was not born. So where was the atom? The atom was inside the Earth. The tree absorbed it as a mineral. Now, 1 millennium back, 1000 years ago, where was the atom? The atom was again inside the Earth, some deeper layer. Okay, not 1000 years, 1 crore years back. Where was the atom? Do you think the atom was not made? No, the atom was there. Probably Earth was not there. The Earth was still being formed. The atom was still there. Okay, now even beyond 1 billion years back, the solar system, questionable. Was it there? But the atom was there. Where was the atom? Maybe 10 billion years back, sometime after Big Bang. Where was the atom? It was roaming around in free universe. It was in some star. It was in some nebula and all that. Look, I am talking about the same atom, the history of this atom. Okay. So how does it came to existence? I have still not defined. Maybe it was formed inside some star as a result of nuclear reaction. So there nuclear astrophysics came into the existence, right? That's the point. Because after Big Bang there was no atom. Atoms were formed after a very large period. Okay. So there was a time when this atom was prepared, was made. I am trying to find the origin. So I have to understand the nuclear astrophysics. Next, where does nuclear structure come into play? Now, look at the sun right now. I am feeling not very uncomfortable, okay. But the thing is that, why is not sunlight very high right now? Sometimes it is very high, sometimes it is very low. It depends on the distance of the earth from the sun, isn't it so? In summertime we are closer, winter time we are far, and all that. There are so many effects. But actual thing is that right now the solar luminosity, what is the reason for that particular value of solar luminosity? Why is it not 10 times larger or 10 times lower? Do you know? If just solar luminosity changes by 0.5, say 10%, our life will become extinct. Okay, so what is the reason? The reason is because of energy levels. The nucleus which are inside the sun as a result of which there is what? Nuclear fusion going on, the energy being released. All of this depends on the structure of the nucleus, where the nuclear interactions are happening. At first there is hydrogen fusion to helium, then helium to carbon, then there is triple alpha process. Now in that triple alpha process, if one of the levels of carbon atom hasn't been there, or it has been say 1 MeV above or below from what it is now, no fusion will have happened after carbon. And not this chalk, not this blackboard, not me, not this smartphone, nothing would have existed. So think, if I ask you in simple layman's term, what is the reason for life? Reason for life was the level of the carbon. It's at that particular energy where it is right now. Had it been somewhat of no more fusion, forget fusion, no more life. So see the importance of nuclear structure. So when you are seeing some nuclear structure, nuclear level scheme, don't just think this is a dumb thing. What happens if this energy level, if it is not at this say 5.1 MeV, if it is at say 4.1 MeV, what will happen? No. Consequences are there, you do not know. The consequences are huge. Just like, for example, if there is a spider moving around and I just wish, suppose all the spiders on this earth vanish because I don't like them, do you think what will happen? Grave consequences. Entire food chain will be affected because they are a part of the food chain. Same old stuff. The level structure, level energy levels inside a nucleus, they are also part of how we are made, why we are made. Okay, so these are all important consequences which research students must know. Don't think that they are just dumb energy levels and all that. They are very important. Okay, and then we have got limits of nuclear stability. Now, see, if this is the value of stability, still we do not know the actual neutron drift line. It is still questionable. Now you will ask me why it is questionable. The reason is that it is very difficult to access. Even as of now, we do not know the actual nature of the neutron drift line. It is still being, lots of experimental investigations are still being undergone at various national laboratories, accelerator facilities to try to understand this. And finally, the exotic nuclei. This we have talked about in great details. So basically the region outside, there is so much region, we do not know. Maybe there will be some other stable zone, but we are unaware because we do not have the technology to go from here to here. Okay, so these are the so many possibilities out there for current nuclear physics research. Basically, I am giving you a sort of quick overview as well as motivating you the importance of nuclear physics. Okay. Now here itself, as we move away from the value of stability, this I have already covered last class. We have observed many things. Say for example, the overall neutron levels shifting compared to proton levels, and as a result, the nuclear reaction and nuclear structure. You have to consider both of them together. Then there is because of this changing nuclear potential, we have got halo nuclei and again skid. Okay, different type of nuclei. There is also borrowing nuclei. This is also a different type of structure for this exotic nuclei. Okay. So overall, when we go to the neutron-rich region, many things change, and then not finally the changing magic numbers. And this is because the potential itself is changing as we move away towards the exotic nuclei region. Okay. So still I have not covered all the topics, but some of the important ones over here for the current physics scenario.